In section 7.2, we look at an alternative method for talking about radicals, and this is the topic on rational exponents. So the word rational just means fraction, and so a rational exponent is an exponent that is a fraction. So we'll start with a basic definition. If you have a number a raised to the power 1 over n, this is defined to be the same thing as the nth root of a. So the denominator of the fraction here is the index of the radical. So for example, if we are trying to simplify 8 to the 1/3 power, this is by definition equal to the cube root of 8. And of course, we know the cube root of 8 is 2. In the second problem, we have 16 to the 1/2 power. 16 to the 1/2 power is the second root of 16. Of course, you know that we don't have to write the 2 here because for a square root, it is understood to be a square root when you leave it blank. And of course, the square root of 16 is 4. So if you know your radicals, rational exponents is just another language in mathematics that we can use to describe those. So to keep going here, 32 to the 1/5 power, this is defined to be the 5th root of 32. And the 5th root of 32 is 2, because 2 to the 5th power is 32. We can also talk about rational exponents when they are negative, and there's no new rule here. This is the same old rule that we had before. So if we have a negative exponent, we define this to be the reciprocal of the same base, but now raised to the positive power. So this is 1 over 25 to the 1/2. Which of course is the same as 1 over the square root of 25. And we know the square root of 25 is 5. So this is 1/5. Now, of course, some fractions do not have a 1 in the numerator. Some fractions will have a number m over a number n, where we do assume that this fraction is in lowest terms. Okay, so we are going to assume that m over n is reduced. And the definition for this, well, it's the same for the bottom number. The bottom number is the index of the radical. So we're taking the nth root of a, but then after doing that, the top number of the fraction is the power we then raise it to. Now, you can do it this way, or you can also raise it to the power first and then take the root second. And so that's what we have here, a to the m power, and then we take the n root of that. So, for example, I'll show you both methods. Take something like 8 to the 2/3 power. So if I use the second definition, this would be the cube root of 8 squared. And we know that 8 squared is 64, and so this is the cube root of 64, and the cube root of 64 is 4. Or the other way to do it is you still have a cube root, but we're going to take the cube root of 8 first, and then we will square it when we get done. And of course, the cube root of 8 is 2, and 2 squared is 4. So notice you get the same answer either way. And so sometimes people will ask, well, which method is better? There really isn't a better method, but I will say that sometimes the second method is easier. And the reason is because if you do the power first, and if that creates a really large number here, that's going to be harder to take the root of when you're done. So it's usually a little bit better to take the root first and do the power second. But the truth is it doesn't matter either way. Now for the rest of today, I'm going to use the second method here. So for our next example, what we have here is the number 9, and the bottom number tells us that we are taking the square root of 9, and then when we're done, we're going to cube that. And so this gives us 3 cubed, and 3 cubed is 27. For the next example, this negative out here is just pretty much a decorative feature. So in other words, you do all this first and you just make your answer negative in the end. So really what I'm focused on is this 2 here tells us that we have a square root of 1 over 25, and then that will be raised to the third power. That's what the top number tells us. And then that negative here just needs to come down in front. And so the square root of 1 over 25 is 1/5. We still have to raise that to the third power. And then again, that negative is still there in the end. And the way we do this, of course, is we apply that third power to the top and to the bottom. And when you do that, 1 to the third is 1, and 5 to the third is 125. And then that negative comes down as part of the answer. So it's -1 over 125. So now we'll just do a few examples involving variables. It's the same definition, so there's nothing really new here, but it does always seem to be a bit more of a challenge when we have variables involved. So for this first one here, we have a 1/3 power here. 1/3 power simply means a cube root, and we are taking the cube root of everything inside the parentheses. And so now we can express this as the cube root, and then I'm going to take this expression and write it as a perfect cube. And so -27x cubed is the same as the quantity -3x cubed. And the reason this is significant is because now the cube root and the third power, those cancel each other out, and all we get left over is what's on the inside, which is -3x. The next example is very similar. So once again, we have a cube root. Everything on the inside of the parentheses goes inside of that radical. And then when we're done here, we still need to square it. So to do this, I'm going to express this thing as a perfect cube. So to express that as a perfect cube would be -2 over 3x squared quantity cubed. That is what this is equal to. Let that sink in for a minute. Make sure you agree, right? -2 to the third is -8. 3 to the third is 27. And x squared to the third, if you multiply 2 times 3, you get 6. So what are we doing? We are taking the cube root of that. And then when we're done with that, we'll square it. So what happens next is when you have a cube root of something cubed, these cancel each other out. And so we are left with -2 over 3x squared, quantity squared. And of course, to do this, we're going to square the top and square the bottom. And this gives us 4 over 9x to the fourth. So it's really important to be methodical as you go through these problems. Okay, moving on to the next example. we have a negative fraction exponent. So remember, when you have a fraction to a negative power, the best way to do it is to take the inside, the fraction on the inside, take the reciprocal, and then that allows you to make the fraction on the outside into a positive number. I think that's the most important first step. And then from here we can use our definition. So we have a square root of 36 over 49 quantity to the third power. And the square root of 36 is 6. Square root of 49 is 7. So we have 6 over 7 to the third power. And now 6 to the third power is 216. And 7 to the third power is 343. All right, for our next problem, what we have here is a common base of 27, and each of those are raised to a fraction exponent power, and we're multiplying these together. So remember your exponent rules. We know that a to the m times a to the n is a to the m plus n. And we can do the same thing here. So using that rule, this is going to be 27 to the negative 5/9 plus negative 1/9. And that is 27 to the negative 6/9, which can be simplified to 27 to the negative 2/3. So from here, all we need to do is apply our rules of exponents. So first of all, we have a negative exponent. So we're going to take the reciprocal 1 over 27 to the positive 2/3. And then we'll apply the definition. The 2/3 power means we're going to have a cube root of that number and then squared. And so this is 1 over, the cube root of 27 is 3. And then we have to square it, and 3 squared is 9. So the answer here is 1/9. And for our final example, we have x plus 3 quantity squared, quantity to the 1/2 power. So again, just use your definition. A 1/2 power is the same as a square root. And so what we have is the square root of x plus 3 squared. And the important thing here is to not make this mistake. Do you all catch the mistake? What do you get when you take the square root of something squared? Well, you don't just get something, remember? You have to put absolute value around it. And so this is just a reminder of that square root property. So in conclusion, rational exponents are no different than radicals. It's just a different way to express the radicals. And they turn out to be pretty important because it gives us a way to numerically quantify a radical. So instead of just having the symbol, we now have a number associated with it. And that allows us to do other things in the future. Okay, let's get to work.